muted. Excellent. So, for today, we are tackling the conic sections in the coordinate plane. We've already dealt with parabolas some, but we're going to touch on that again. And the two other conic sections you may see on the ACT are the circle and the ellipse. And if you want to look at his notebook of math stuff, it would be on page 11, is the notes that tie into this. So, parabola, again, we've talked about the ax squared plus bx plus c form. We've talked about the factored form. So ax plus b, cx minus d. And for the majority of conic sections, you'll frequently see it in what's called vertex form, which is the a x minus h squared plus k. And so all of those are parabolas, all of those have their different uses. But the reason it's called a conic section is that if you took a 3D cone and took a slice that was perpendicular to the table or straight up and down on this cone that was sitting on the table, it would, no, sorry, I'm thinking wrong. It would be parallel to the slope of the cone would create the parabola. So that one's what would be here. The ones that we haven't talked about as much are a circle. And a circle is the collection or the locus of all the points that are equal distant from one center point. We use compasses to draw that in geometry, but in the math world, it breaks down to the idea that x squared plus y squared is equal to radius squared. And we can change this location, x minus h squared plus y minus k squared is equal to radius squared. And so this, just like this vertex form, by changing what happens to that x coordinate before we square it, this is where we get that horizontal shift. And if we change y, that creates a vertical shift. And then the r stands for the radius. And so a very classic question would be, what is the formula of a circle with a radius of 7 that is centered about the point 2, 3? So radius equals 7, and the point is 2, 3. This point will go with our x, and if we want it at 2, we have x minus 2. And so it is that opposite sign that, again, I'm hoping you have seen with the parabolas. And so it becomes x minus 2 squared plus 3 affects our y, our vertical. And so it's y minus 3 squared. And it equals, sometimes you'll see it as 7 squared, sometimes you'll see it as 49. Both of them are okay, but I can't guarantee what form the test will have for options, and so be familiar with both of them. that you are frequently taught circles in, but I'm going to introduce a second option. The second option says, what if instead of leaving this as radius squared, we decide to divide by this radius squared. Radius squared divided by radius squared becomes 1. And this becomes x minus h squared over radius squared plus y minus k squared over radius squared. In this form, much less common or traditional, but what it does is it helps us see the transition into the ellipse. And an ellipse, think of it as a squished circle. An ellipse is going to have this curved trajectory orbit, but rather than having one single radius, the distance wobbles. And so in an ellipse, we are interested in the extremes. How high is it top to bottom? How far is it side to side? And so this, I'm trying to make sure, okay, we use A and B. So this, rather than having a single radius, we have the vertical wobble and the horizontal. And so in a circle, bad circle, but in a circle, that wobble is the same. It's the radius and the radius. And so these two are the same number, which is why we frequently just stop it here. But within an ellipse, that number is different. And so the top is exactly like our circle. We're going to have x minus h talking about the horizontal shift. We're going to have y minus k talking about the vertical shift. But it's going to be equal to 1. And for our x, if this is the distance a from the center over to the outside, our horizontal distance is divided by that a squared. If this is the distance vertically represented as b, then our vertical is represented by that wobble, or that difference. The idea is when a goes to 0, because at this point, whatever we put in for x cancels out by the vertex and it just disappears. And this is what happens at that largest point, that widest point, right there. When this first part completely disappears, it's at the highest or lowest point. When this part disappeared, it's at the farthest left or right. And so, parabola, I'm hoping very comfortable, but getting into this idea of the vertex form, this transition, that applies to both horizontal and vertical within the circle. And then this wobble at the bottom, how far changing left or right, how far changing up or down goes into the ellipse. Okay. One of the classic problems is something that looks like this. A bad drawing. Ellipses are harder to draw than you think. I'm looking like scary eye. But for our small circle, the idea, this is going to be centered about the origin. We don't have to deal with the shift, thank goodness. But the small circle of the equation says that x squared plus y squared equals 4. For the large circle, the equation says that x squared plus y squared is equal to 25. What would the equation of the ellipse be? I'll give you a couple minutes to work at it, and then we'll move forward. So, filler discussion while people are still working. There is a fourth conic section called a hyperbola. You will work with those in your classes, but they are not on the ACT. The only difference with a hyperbola is that they changed this plus into a minus sign, but the difference in the graph is very, very drastic. And so it has to do with orbits versus gravity wells. But for the purposes of this problem, we are interested in these 4 points. Those are going to be the extremes of our ellipse. So, because it's centered at the origin, anytime you've got something centered at the origin, you don't have to worry about horizontal or vertical shift, and so all we have is x squared plus y squared. It's always equal to 1 with an ellipse. And so all we need is to divide by our horizontal and vertical wobble. So, what is our distance side to side here gonna be?
25.
Close. We're gonna use 25. The distance is technically 5, but since we turn right around and square it again, we want to use that 25. And what is our vertical? It's square root of 4. This is just 2. But again, we're using the 4 again because it is the b squared. This is just over 4. And so it's using the 2 pieces of that circle to combine together into an ellipse. And so again, the more you understand that's where those pieces are coming from, the easier it is to remember this formula rather than trying to just memorize it without context. Alright, I'm gonna take a minute to draw this one out because I feel like it's important, even though it's gonna take me a second to put the options up there. So, I'm going to give you the equation and ask you to start trying to graph it on your own, but then I am gonna have the multiple choice options for you. And so the question asks to graph the system of inequalities where x plus 2y is less than or equal to 6 and 3x squared is greater than 12 minus 3y squared. And the question is, which one of these graphs is the correct graph? But I would get started with that. Any graphing that you want to do or solving that you want to do in order to graph it. So, I'm all for process of elimination. Which one of these graphs can we reject outright?
The solid line circle.
Solid line circle, because here our solid line is on the linear, our strictly less than greater than is on the circle, and so this one's out. What else can we do to help us along?
Positive slope.
Okay,
Yeah.
because you're going to end up subtracting x and dividing by 2. Yeah, positive slope, out. Good. From there, again, I would be giving myself a pretty good note. This is going to end up being y less than or equal to negative x over 2 plus 3. So y is less than, below the line, this one's also out. And so all of those we've been able to do without being really able to graph a circle at all. That's okay. What else should we do to that circle equation to make our life easier?
Divided by 3.
divide by 3, make it a lot prettier. So what we have is x squared greater than 4 minus y squared, or in other words, x squared plus y squared is greater than 4. So we're down to these two. The idea is either the graph crosses the circle or the graph doesn't cross the circle. What would be the point to focus in on that? At this point, I would probably do a tiny graph of my own, just for my own reference. We've already figured out the shading, and the shading is essentially the same, it's just where this line is positioned, so we don't need to worry about that as much. The idea is, this graph, what's my y-intercept? 3. So it's crossing at 3 and going down 1/2. Where is our circle going to be touching that x-axis? At 2. Remember that this 4 is the radius squared. That means the radius is only 2, and that's the highest it gets. It also wobbles 2, 2, 2, and 2. And so this is our circle. We want the ones where it is not crossing through the circle. So not a lot of graphing on that one. You could possibly run it through a graphing calculator, but by the time you have done all the solving to get it to a point that you can, it's really not worth it. So wouldn't recommend a graphing calculator on that one. All right, what did I do with it? There it is. So again, that one was a little bit long from the point of view of writing it on the board, but I felt like it was an important one to talk about because it has a lot of that breakdown, understanding what the pieces are doing. And we're halfway there. Okay. So, in the standard coordinate plane, y is equal to 2x squared plus x all over x. And just give this a rough sketch. What would the graph look like? So this one looks big and daunting, but everything is divisible by x. And so it very quickly goes to 2x plus 1 is all that is. With the caveat that x cannot equal 0, because X caused a divide by zero error in the original. And so you have to keep the exceptions, but say, as long as X isn't zero, it's gonna look exactly like this line. Nothing big happening at all. And so for our graph, our y-intercept would be at 1, but at 1, we draw a circle, a hole, and say, that one doesn't quite work. But for everything else, we go up 2 over 1. Here's my graph. And so even though they may look scary, maybe it's quadratic, maybe it's a rational function, all the things, occasionally they cancel down to the straight line. So don't get too flustered before you stop and say, hey, wait, I can make that go away. All right. So we have a parabola. It is centered with the axis of symmetry at the y-axis. I'm just bad at drawing. But the idea is that we have a rectangle inscribed inside this parabola. And they tell us that y equals 6 minus 2x. And it says, let a represent any value of x such that it's between 0 and the square root of 3. So we're using this interval right here. X can be anywhere along this line, it just happens to be drawn as such. And so this distance right here is a, this distance right here is 6 minus 2a squared. Sorry, that one was my fault, that should have been x squared. Bad copy. So, it asks you to express the area of that rectangle in terms of A. So, key to this one is to recognize that the entire length of this side would be 2a. And so you're multiplying 2a times 6 minus 2. Can't write. And so you would be multiplying that in. And we end up with negative 4a to the third plus 12a. All right, on this one's more straightforward. I would expect to see this if they throw a circle problem at you. This one's a very fair game circle problem. It just asks for, in the standard XY coordinate plane, the vertices of the square have the coordinates 0, 6, 0, 6, 6, and 0, 6. Which of the following is an equation for the circle that's inscribed in the square? Or write the equation of this circle that is inscribed in the square. So remember, you're looking at where is the center and what is the radius in order to write the equation of a circle. All right, so first off, where is my center? What is our coordinate for our center?
3, 3.
Yeah, we are both over 3 and up 3 because it's the middle of both sides. So how do we translate positive 3 and positive 3 into the equation? You've got it right, be brave. What do we write in our equation?
Oh, x minus 3.
Yeah.
minus-
Because it's the opposite of the sign of our center. And so if this is positive 3, we have minus 3 and minus 3 in our equation. And then finally, what was the radius of our circle?
3.
More threes. Threes all over the place. So, is that correct? No. What do I need to do to finish it?
3 squared.
You gotta square the radius. Whether you write it as 3 squared or write it as 9, it's really a toss-up. I have seen problems with both of them, and so it's hard to guess what form you'll see on the test. In this case, it was the 9 in the options, but that is that. All right, this one is not truly a circle question. Honestly, they're hard to come by on the ACT. You may see one, but there's not that many. And so this one kind of falls into the same category and works that same part of your brain. And so they say, let the function a be defined as f of ab is b squared minus a. And they want you to calculate it using these pieces. What would that value be? So what would be the first thing to notice on this problem? First thing to notice is that they pull as a switcheroo. They say A and then B, but within the equation, B is what's getting squared, A is alone. And so that tendency to try and first in, first out, go the same order of what they offer to you is one of those rushing stumbling blocks that's really easy to make when you're crunched for time and you're trying to get through the test. And so this is the piece that's going to end up being squared. You end up with x squared minus 2xy plus y squared. And now we are subtracting this piece. The whole thing, x squared plus y squared. The subtraction, you can distribute it, is now applying to both pieces. X squared minus x squared goes away. Y squared minus y squared goes away. Only negative 2xy remains. Once again, I don't want to be too hand wavy. Does that make sense where that one came from? But truly, that reverse order trips people up more than you want to admit. It just messes with how your brain wants to tackle the problem. All right, so on this one, we've moved back to parabolas. It tells you that the three parabolas graphed in the standard xy coordinate plane are a family of parabolas. A general equation that defines this family of parabolas contains the variable n in addition to x and y. For one of the parabolas shown, n equals 1, another n equals 2, a third n equals 3. So what would the general equation in terms of n be? And so our options are nx squared plus 1, 1/nth, x squared plus 1, x squared plus n, negative n, x squared plus 1, or negative 1/nth, x squared plus 1. Shouldn't be too much calculation on your end, just which one of those equations describe what is being graphed. Right. So negative would have flipped our parabola. Remember that if an equation is positive, it's smiling or opening up. If it's negative, it's frowning or opening down. Since these are opening up, everything with the negative is out. And so that's one of the first landmarks. Second, this is acting as our y-intercept. The plus 1 is a constant, and so we are not shifting up or down. We're staying constant, and so this one is out. Finally, as our n is getting bigger, our graph is growing more rapidly, versus if it were a fraction, if this were getting bigger, it would be flattening, it would be slowing it down, making it more wide. And so this is our equation. All right, for the last 10 minutes, we've got a few options. I can take any questions that you have, whether from homework or something else. I can take, hey, can you come up with another parabola problem, even if it's not officially ACT, I can give you a couple, or a ellipse problem or a circle problem, or I have more geometry-based circle problems. Where do you feel you would like more practice? So the first question is, anything from homework, book, previous? No? Okay. Anything that we've covered so far, would you like another ellipse or circle practice problem? Okay. Then I think we'll move on to the geometry ones again, because I think they are useful. This one's going to challenge my art skills. Basically, we have a cube, and it's contained within a sphere. Drawing skills are not great. It's supposed to be going through that corner. Basically, it's a cube inside a ball, and it's touching all the corners. So, the edges is 4 centimeters long. And the question is, what is the radius of the sphere? My drawing is quite bad. If you want to see their picture, it might help a little bit. So the idea is, this is 4 centimeters. How do we find the radius from the center to a corner? Not quite, but you're on the right track. Actually, you might be right. Now I'm gonna have to double check. So initially, 4 square roots of 2, pretty straightforward. When we have the block sliced open, if this was the sliced face, this diagonal is what we're trying to look at, but this slice right here would be 4 square roots of 2, and this would still be the 4 of across the way. And so 4 and 4 is 4 squared plus 4 squared is 16, plus 16 is 32. And so you can skip the line a little bit. This one is, this squared equals 32, this equals 16. So we have the square root of 48, or 4 square roots of 2. No, I've lost it. What is the square root of 48 simplified? My brain is.
4 squared root 3.
There it was, wasn't it? So that is our distance from this upper corner to this lower corner. But what did they ask us for?
Radius.
They asked us for the radius. And so we just need 2 square roots of 3. Those eyeballs say I did some magical hand waving.
I get that. I think I get that.
All right, closing with one last circle problem, hopefully relatively simple. The idea is we've got a circle, we have a diameter across the circle, and we have an angle of 60 degrees. So they asked the shortest distance along the circle from MP to P, which is here, M to P, distance along the circle is this, compared is what percent of the distance along the circle from M to N. And so they are comparing this arc length to this arc length. What percent would it be? Oh, my degree sign is terrible. I'm sorry, that looks like an 8. This is 60 degrees. Bad handwriting. So the first question, how many 60s are there in a complete circle? 6. So this is just 1/6 of the circle. How much of the circle is the diameter?
3.
3/60s,
Yeah.
but it's 180 or 1/2 of the circle. And you're saying you need 3 of these to get to one of those. So when we're looking at the percentage of MP to MN, that's going to be 1/3 or 33.33%. All right. With that, we will pack up. Is there anything else I can answer for you before you go? Did you go in too many circles on that one?
I forgot what the question was.
In that case, I blame my lousy copying skills. Someday I would love to be able to just project problems up, but for now, this is what we've got.